Welcome to emergentbehaviors.com channel. Today we're looking at SOAR, a way to get models to generate their own practice problems because high-quality external training data is increasingly a bottleneck. The work comes from Sundaram and colleagues at MIT, with collaborators at Metafair in a paper titled Teaching Models to Teach Themselves, Reasoning at the Edge of Learnability. The informal idea is simple: make up your own homework, then learn from it. In this talk, we'll unpack three things. First, why reinforcement learning with verifiable rewards can hit a hard plateau. Second, how SOAR's teacher-student setup is designed to push past that edge. And third, what the experiments show about stability, diversity of generated problems, and transfer to new tasks. Next, we'll zoom in on the plateau itself. What happens when the model just never succeeds and the reward signal disappears? In this slide, we framed SOAR around a practical bottleneck. You can't always get enough high-quality external data. But even if you switch to reinforcement learning with verifiable rewards, where the model gets credit only when it's objectively correct, you hit what this slide calls the cliff of unlearnability. Here's the issue. RLVR works as long as the model sometimes succeeds. Once you reach tasks where it never succeeds, the reward collapses to zero. That's exactly what the dataset example illustrates. On fail at 128 math, the model attempted the same kind of problem 128 times and failed every time. Empirically, that looks like a 0% success rate. And with zero successes, there's no reward signal, so the gradients have no direction. Training doesn't just slow down, it flatlines. Next, we'll see why just find intermediate problems isn't so simple. So if RLVR hits a cliff, why not just train harder or add more data? This slide's three columns show the bottleneck. Curated intermediate problems are scarce, and at the frontier, you can't reliably handpick enough stepping stones that are close enough to help, but not so hard that learning stalls. That leads to a tempting shortcut: intrinsic rewards. Let the model generate problems and grade itself, rewarding novelty, length, or some proxy for difficulty. The catch is those proxies are easy to game. The model learns to optimize the score, not to produce useful practice. And that's the failure mode named here. Diversity collapse. Instead of rich intermediate signals, you get repetitive, easy nonsense that looks rewarding but teaches nothing. Next, we'll pivot to a key claim. Even if a model can't solve the hardest problems, it may still be able to teach toward them. This slide makes a subtle claim. Even when a pre-pranked LLM can't solve the hardest target problems, so RLVR gives it essentially zero reward, it may still be able to generate easier problems that look like those targets. Not the final exam question, but nearby exercises, simplified versions, partial subskills, or constrained variants that share the same structure. The goal then is to extract that latent pedagogical knowledge and use it to build an autonomous curriculum, stepping stones that gradually bridge the gap from what the model can do today to what it can't do yet. And the key distinction is this: solving and teaching are different skills. A model might fail as a solver at the frontier, yet still implicitly know how to teach its way toward it. Next, we'll see how SOAR operationalizes that idea with explicit teacher and student roles. So here's SOAR. Self-optimization via asymmetric RL. In the diagram, there are two roles. The teacher doesn't solve the exam directly. Instead, it writes a curriculum, practice problems, and feedback. The student then trains on that curriculum in a short inner loop. Think on the order of 10 update steps, and we check whether it actually got better. The key is the asymmetric reward. The teacher is not rewarded for producing questions that look elegant or seem difficult. It only gets reward if after the student's brief training, the student improves on an external exam set, the hard validation problems that previously caused the RLVR cliff. That's what the two loops mean. The outer loop optimizes the teacher with RLO, and the inner loop trains the student with RLVR, validated against a hard set. Next, we'll contrast this grounded reward with intrinsic proxies. Here's the secret sauce: grounded rewards on the left. Intrinsic rewards are just proxies. Signals like, "That seems like a good question," or "This looks difficult." The problem is they're easy to fool. A teacher can learn to write long, novel, or flashy questions that score well on its own rubric, without actually helping the student learn. Grounded rewards flip that. We measure progress directly on the target hard problems, treating the hard dataset as a black box reality check. The teacher only gets credit if, after the student trains briefly on the generated curriculum, the student's performance on that external hard set improves. Operationally, this forces the teacher to generate training data that produces measurable gains, not just data that looks good. Next, we'll see what that buys us in results. Read the headline here. SOAR training yields about a plus 9.3% improvement compared to direct hard-only training, and roughly a threefold boost over base inference. So what's actually driving that jump? It's the teacher's synthetic promotion questions. Remember, back in the asymmetric setup, the teacher isn't rewarded for sounding smart. It's rewarded for moving the student. These generated exercises target the exact subskills the student kept failing. So a short burst of training finally unlocks capability on the real hard problems. And notice how the metric is reported. Accuracy as pass at 32. That's important. We're not grading the model on the synthetic curriculum. The gains are measured on the hard evaluation set, the external exam, so the improvement reflects genuine transfer, not memorization. Next, we'll see why this grounded approach is also far more consistent across random seeds. Now look at stability across training seeds. Conceptually, each curve is the same method rerun, with a different random initialization and sampling stream. With intrinsic reward training, those curves spread out dramatically. One seed stumbles into a helpful curriculum, another collapses into a dead end, and a third succeeds by gaming the proxy. That's the slide's core claim. Intrinsic rewards are fragile, and they invite reward hacking. The teacher learns to optimize the metric, not the student's actual learning. Grounded rewards behave differently. Because the teacher only gets paid when the student improves on the external exam set, the signal is anchored to real performance, not a loophole-prone surrogate. So across seeds, the learning curves cluster tightly, and the gains are reproducible. Next, we'll push on an apparent paradox. Many generated solutions are wrong, yet the questions still help. Notice the two key numbers on this slide. Only 32.8% of SOAR-generated questions come with fully correct solutions, but 63% of them are still mathematically well-posed. That gap is the point. Even when the answer key is hallucinated, a well-formed problem can still teach. The student gets a learning signal from the structure itself, setting up the right variables, constraints, and transformations. So training isn't pure noise. And this connects back to the plateau we talked about earlier, when direct grounded rewards are sparse because the hard problems are basically unsolved. You need intermediate practice that creates gradients. Structured questions, even imperfect ones, can move the student toward regions where the final exam problems become solvable. Next, we'll see how grounding also keeps the teacher from collapsing into repetitive, one-trick curricula. Now compare these two teachers side by side. With an intrinsic reward, the model quickly falls into a rut. It discovers one kind of question that scores well on the proxy, and then repeats it. The curriculum looks busy, but it's narrow, and you can see that collapse in the diversity metric. The Venn score is just 10.8. SOAR looks different. The questions stay varied, and the Venn score jumps to 28.3. That's not an aesthetic win, it's causal, because SOAR's reward is grounded in the student's performance on the external exam. A one-trick curriculum gets punished automatically. If the training data is too narrow, the student fails the final exam, and the teacher doesn't get paid. Next, we'll see why this diversity also transfers beyond the original benchmark. Now, look at the transfer result on this slide. When the teacher optimizes questions using math and HARP as its grounded targets, the student's performance on Olympiad bench rises by about 6 percentage points over the baseline. That's the accidental genius idea. The teacher was never explicitly rewarded for Olympiad bench. Yet the curriculum it discovered still builds reasoning pathways, how to set up constraints, choose transformations, and navigate multi-step proofs that carry over to a different, harder distribution. And this matters because it argues against teaching to a narrow test. If SOAR were just overfitting to the reward set, we wouldn't expect clean gains on an external benchmark. Instead, we see evidence of more general mathematical competence emerging. Next, we'll sharpen this point. Generating effective stepping stones is not the same as solving the hardest problems directly. Here's the key point on this slide. Generating effective stepping stones is a different skill than solving the hardest problems directly. A model can be mediocre at the final exam and still be excellent at proposing the right intermediate exercises. The ones that expose structure, build subskills, and create usable gradients. That's the impact claim. SOAR lets us extract pedagogical signal from the model itself and use it to push the student past its own reasoning plateau. The teacher doesn't need to be an Olympian, it needs to be a good coach, and SOAR's setup makes that precise. The teacher is evaluated by student improvement on an external target, not by the teacher's own solve rate, so even a non-elite solver can be valuable if it reliably helps another model learn. Next, we'll see why this matters most when there are no human solutions to learn from. Now zoom out to the North Star. For truly novel problems, think something like the Riemann hypothesis. We can't count on a backlog of human solutions as training data. There is no answer key to imitate, and waiting for more labeled examples isn't a plan. That's why the core takeaway here matters. SOAR shows a concrete mechanism for making progress anyway. By rewarding a teacher for generating stepping stones that measurably improve a student on a grounded external objective, the model can mine its own latent knowledge, discover curricula, and push beyond a plateau even when direct solutions are out of reach. So the message is simple. We may not need more data, we need better ways to exploit what models already know. That's the end of our presentation today. Huge thanks to the author of this research paper for their hard work. Thanks for your time and watching this video. Leave your thoughts in the comments and check our blog and source link for details.